Good morning to one and all. Today, we are going to solve a problem on economic load dispatch with the loss coefficient, like that is a B loss coefficient with the loss factor we are considering. Actually, we have solved many problems in our previous classes. So compared to that problems, this problem has it involves some more steps. But you should understand what is this loss problem and the formulation. Take down this problem. A system consists of two plants connected by a transmission line, and the load is at power station plant 2. So the system is given here. Actually, this is the generating station, and here they are telling like load is at bus 2. Okay, so load is at plant 2 as shown in the figure. There are two plants are there, but the load is connected to the plant 2, and plant 1 and plant 2 connected together. And usually there will be some transmission line losses will be there because plant 1 and plant 2 is connected with a transmission line. Say, for example, it is some n kilometers. You take the numbers, whatever you want, but there might be some loss factors involved in this transmission line. So the data for loss equation 1 consists of information that 200 megawatt transmitted from plant 1 to the load results in the transmission loss of 20 megawatt. Find the optimum generation schedule considering the transmission losses to supply the total load of 204.41 megawatt. So total load of 201.41 megawatt, in the sense this is the demand. Also evaluate the amount of financial loss that might be incurred if at time of scheduling transmission losses are not coordinated. So they want to calculate the financial loss at the time of scheduling transmission losses are not coordinated. Okay, transmission not loss are not coordinated. We need to find out the financial loss. Next, the incremental fuel cost characteristics of plant 1 and plant 2 are given in this. That is DF1 divided by DP1 is equal to 0.025 P1 plus 40 rupees per megawatt hour. Next, DF2 divided by DP2 is equal to 0.05 P2 plus 16 rupees per megawatt hour. So this figure, that is plant generator 1 and generator 2 from plant 1 and plant 2, already we have discussed. So how to solve this problem? So first, P loss equation, PL is equal to this matrix P1 into P2 matrix into B11, B12, B21, and B22. This is the B loss coefficient matrix. And here this P1 into P2. So while just multiplying all these matrices, you'll get the power loss equation like this. PL is equal to B11 into P1 squared plus 2B12, P1 P2 plus B22 P2. So this is the power loss equation. Now, since the load is at bus number 2, because already given in the problem clearly, so what they given is load is by considering load is at power plant 2, that is shown in the figure. So since the load is at bus 2, that is power plant 2, so P2 will not have much effect on this power loss. So PL equation only, we need to neglect this P2 here. So only P1 factor alone will comes under this loss coefficient equation. So PL is equal to B11 into P1 square. Take this as equation number 1. Next, PL is equal to 20 megawatt. That is power loss equal to 20 megawatt given in the problem itself. That also you need to take. So here you need to substitute PL is equal to 20 megawatt here. So 20 is equal to B11 into P1 square. So P1 also given in the problem, that is 200 megawatt. So here it is given as the data for loss 1 equation consists of information that 200 megawatt transmitted from plant 1 to load results in the transmission loss of 20 megawatt. So 200 megawatt is transmitted from plant 1 to the load. That also given. So P1 is equal to 200 megawatt, that is given in the problem. Just to substitute here and you calculate B11. So B11 is equal to 20 divided by 200. So that is nothing but 0.0005 megawatt inverse. So this is the B11, that coefficient, the loss coefficient. Now you need to substitute B11 in the equation number 1. Okay, so if you substitute in this equation number 1, PL is equal to 0.0005 P1 square. So this is the power loss equation as of now. So now what we need to do is, what is the condition for optimal dispatch? L1 into DF1 divided by DP1 is equal to L2 into DF2 divided by DP2 is equal to lambda. Take this as equation number 2. Since PL is the function of P1 alone, that is a power loss equation is a function of P1 alone. So we need to like L1 is nothing but L1 is equal to 1 divided by 1 minus dou PL divided by dou P1. So we need to differentiate dou PL with respect to P1. You'll get this equation is there now, PL equation. So you need to differentiate this equation with respect to P1 now. 2 into this 0.005 will come here. So that is nothing but 0.001 into P1. Okay, take this as equation number 3. Similarly, you need to calculate L2. L2 is equal to 1 divided by 1 minus dou PL divided by dou P2. So here dou PL divided by dou P2 is equal to 0 because PL equation don't have P2. P2 function, that is a power generating 2 function. So it is 0 here. So simply it is 0 here. So 1 divided by 1 minus 0 is 1. So L2 is equal to 1. Take this as equation number 4. Now substitute L1 and L2 in 3 and 4. Okay, so that is 3 and 4 in equation number 2. Equation number 2, what? That condition for a optimal dispatch, that is L1 into DF1 divided by DP1 is equal to L2 into DF2 divided by DP2. Just substitute, okay, here. So here we are substituting and equating and simplifying this. While simplifying, we'll get the equation like this. That is 0.041 P1 minus 0.05 P2 plus 0.0005 P1 P2 is equal to 2. Take this as equation number 5. So while doing this problem, if you miss even 1 0 here, the whole problem will go wrong. So you need to be very careful while choosing this after decimal, how many digits are there, zeros, everything you need to take correctly. So this is the equation number 5. This is nothing but function 1 of P1 comma P2, that is nothing but 2. That we are taking as F1 of P1 comma P2 is equal to 2. So this function, this equation, that is nothing but we are taking this first function, that is F1 of P1 comma P2 is equal to 2. So similarly, so here P1 plus P2 is equal to PD plus PL. That is a power. That is a power balance equation. Power generation is equal to demand plus losses. So what is P1 plus P2? That is given in the problem. That is demand is given as 204.41 megawatt. That is already given in the problem. PL also given, we calculated. That is 0.0005 P1 square. Okay, so here just simplifying this equation, we'll get the equation like P1 plus P2 minus 0.0005 P1 squared, that is equal to 204.41. Take this as equation number 6. This is nothing but F2, that is function of P1 comma P2 is equal to 204.41. So while why we are converting this as a function, because we are going to solve this with the Newton-Raphson method. This equation is complex to solve. Okay, with a normal method. Say, for example, this 5 and 6 equation, if you take this equation is complex to solve with a normal method. So that's why we are going for this iterative method, like Newton-Raphson method. There are n number of iterative methods are there. With that, we have chosen only Newton-Raphson method. So you can also solve with the optimization techniques and all. But here for the simplification, we are taking this Newton-Raphson method because Newtonian's method is a very accurate method for solving the problem. But even and also iteration, little bit iteration it will take, but it will the answer it will give very correctly. Okay, so for reducing the iterations and all, we are going for some other optimization techniques to solve this problem. So as of now, we are taking this Newton-Raphson method to solve this particular problem. So what is the Newton-Raphson method? Already we discussed. So here, this change in function del F is equal to J into del P. So already we discussed enough this method in our previous classes. If you want, you just you can watch that Newton-Raphson method also. That is already there in our channel. So here, change in the function, del F is equal to here this function that is from the equation 5 and 6. So this is one function f1 of p1 comma p2 is equal to 2. So that function we are taking as 2 minus f1 of p1 comma p2. Similarly, this function we are converting as 204.41 minus f1 f2 of p1 comma p2. So now to find the initial estimate, let us solve the problem without losses. First, we are solving the problem without losses. So the same, the incremental fuel cost df1 divided by dp1 is equal to df2 divided by dp2 is equal to lambda. That is the optimality formula that already we derived in our previous classes. So here, just this function is given incremental fuel cost df1 divided by dp1 and df2 divided by dp2 is given. Just you need to substitute and simplify. You'll get the equation like this. That is 0.025 p1 minus 0.05 p2 is equal to 2. Take this as equation number 7. So already we have previously like p1 plus p2 is equal to 204. That is PD. Generation is equal to demand. So PD already given in the problem. P1 plus P2 is equal to 204.41 megawatt. So you need to solve this two equation and you need to calculate what is the P1 and P2. So here we are taking this P1 and P1 not and P2 not. That is initial values like that we are taking. So we are taking P1 0 and P2 0. So while calculating, we are getting P1 as 162.94 megawatt. Similarly, P2 we are getting as 41.47 megawatt. So you just tell in the comment whether you got the same answer or not, or any other different answers you got. So here, now what we are doing is we are going for the first iteration, that is change in the function. Del F naught is equal to this 2 minus F1 of P1 naught, comma P2 naught. Next 204.41 minus F2 of P1 naught, comma P2 naught. Now substitute whatever we calculated, P1 naught and P2 naught in this that equation 5 and 6. So you'll get this function. Just substitute this and simplify this. You'll get the first change in the function as minus 2.94. Similarly, second function as 13.27 in that equation. Just you need to substitute P1 naught and P2 naught in this same equation, that is 5 and 6, and you need to calculate this change in function, that is del F naught. So this is the del F naught matrix, that is minus 2.94 and 13.27. Now what is the change in the function? That is a change in the function del F naught is equal to J into del P, that is change in the power. So Jacobian matrix you need to calculate. So del P, that is change in the power, is equal to J inverse of del F naught. Okay, so if this is that is del F naught is equal to J into del P, then del P is equal to J inverse into del F naught. That's all. So what is J here? J is nothing but the Jacobian matrix. So Jacobian matrix already you know, del F1 dou F1 divided by dou P1. Here dou F1 divided by dou P2. Here dou F2 divided by dou P1. Dou F2 divided by dou P2. That is, we are differentiating the function 1 with respect to P1 and the function 1 with respect to P2. Similarly, function 2 with respect to P1 and function 2 with respect to P2. Just we need to calculate all this change in the function. So first we are calculating del F1 divided by del P1, dou P1. By taking P2 as that already calculated value, P2 not already we calculated, no, that is 41.47 megawatt. Just substitute here and you'll get the change in the dou F1 divided by dou P1 is equal to 0.0430. Similarly, dou F1 divided by dou P2. Just to differentiate that function and you need to substitute P1, P1 not. P1 naught value, that is already we calculated, that is 162.94 megawatt. You just substitute this value, you'll get a minus 0.0418, that is dou F1 divided by dou P2. Similarly, dou F2 divided by dou P1 is equal to 1 minus 0.001 P1 naught. So P1 naught already we calculated, just substitute it. You'll get a 0.8370. Similarly, dou F2 divided by dou P2. So dou P2, that is, I think, 1 minus that function will become 0 because no P2 in this function F2. So that function that becomes 0. So it will become 1. So Jacobian matrix we framed with all these things. So Jacobian matrix equal to 0.0430 minus 0.0418, 0.8370 and 1. Now del P, that is change in the power we need to calculate. So that is nothing but J inverse into this the function, change in the function, the del F naught. So J inverse you need to calculate. So A inverse, what is the J inverse means 1 by modulus of J into adjoint of J. 1 by modulus of U. So modulus of J, you know, so this and this you need to multiply and you need to change this sign and you need to calculate. So this element and this element you need to multiply and minus of this element and into this element. So you'll get a 0.0430 plus 0.0349. Okay, so if you're doing for taking adjoint for 2 cross 2 matrix, it's very simple. If it is 3 cross 3 matrix, you need you have to do more. But 2 cross 2 matrix, very simple. What you need to do is you need to interchange these elements. Okay, you just interchange those elements. This two elements you need to change the signs. That's all. That is the adjoint of 2 cross 2 matrix. So that's what we did here. We just interchange those elements here. That is 1 has here and 0.043 has here. And here this two elements, just you need to change the sign. That's all. So we adjoint, we calculated into this change in function. You just need to multiply this and you need to simplify. Take your scientific calculator. You just simplify this and change in power. We are getting it as del P1 naught and del P2 naught is equal to matrix of minus 30.620 and 38.9138. That is the change in power. So what is this is the change del P1 naught and del P2 naught. So what is P1 dash? P1 dash and P2 dash matrix is equal to P1 naught into P2 naught matrix plus change in P1 naught plus the del P2 naught matrix. So this you need to add. So this elements you need to substitute and you need to add. Okay, just you need to substitute P1 naught, P2 naught already we calculated. Del P1 naught and del P2 naught also already we calculated. Just substitute it and you'll get a P1 dash and P2 dash is equal to 132.32 megawatt and P2 dash equal to 80.3838 megawatt. So this is for the first iteration. So similarly, you do it for some 4 to 5 iterations so that this value will get converged. Then only you need to take. So for time being, because we are doing with the hand calculation, no. So time being, we just stopped the up to 5 first iteration, but you just take it as a homework, whether you do by hand calculation or you program this algorithm and do it with a Python or a like MATLAB program, whatever the platform you choose, you just calculate it later. But as of now, the first iteration values are here. That is P1 is equal to 132.32 megawatt and P2 is equal to 80.3838 megawatt. So with these values, what we are doing is we are going to calculate the fuel cost. So how to calculate the fuel cost? Already we have seen the similar problem because dF1 divided by dP1 is given. Now we need to find out the F1. So F1 is equal to integration. We need to do the integration. There it is differentiation is given. So F1 alone, if you want to calculate, you need to integrate. That's all. So F1 is equal to integration of. So here you need to remember. So this is for a lossless. So lossless already we calculated, no? For without losses, we already calculated and we already calculated what is P1 naught and P2 naught. Yeah, without losses. So without losses, we are taking in the downscale. Like in the integration, we are taking the downscale. So why? Because they asked to calculate in the problem. So the data given in the problem, they asked to calculate for losses line. Without losses, they asked to calculate what is the loss incurred. that they asked to calculate. You go to the problem means you understand clearly what they asked is find the optimum generation schedule to the considering the transmission line to supply the load of 205 megawatt and also evaluate the amount of financial losses that may incurred if at the time of scheduling transmission losses are not coordinated. So transmission losses are not coordinated that they ask the financial loss. So that's why we are taking in the integration, whatever we got P1 and P2 value, that we are taking in the downward scale. Okay. So here P1 and P2 we got no without losses, P1 and P2 we got. So these values we have taken in the integration in the downward scale. So that we are taking. So here integration we are taking this. Yeah, so while integrating this 162.94 megawatt without loss line that we are taking here with the losses, we already calculated as 132.32 megawatt. Here the previous thing we calculated that we are taking the upper scale. So that we are differentiate. This is DF1 divided by DP1 into DP1. So we are integrating this. So integrating means 0.025 P1 squared divided by 2 plus 14 into P1. So you need to substitute this upper value and lower value. Okay, 162.94 and 132.32. First, you need to substitute upper value and minus this lower value. While simplifying this, we'll get the answer as 2071.3372 minus 2613.0280. That is fuel cost F1 is equal to minus 541.6908 rupees per hour. So minus in the sense, this is the losses. The first fuel cost is loss. So next we are calculating the fuel cost 2. So here also similarly in the downward scale we are taking this without losses. Already we calculated P2 as 41.47 megawatt. Similarly, upward scale we are taking this with the losses that we calculated recently. Yeah, P2 as 80.3838 megawatt. So here that we are taking this upper scale. So similarly, DF2 divided by DP2 that is given in the problem, already given in the problem. That function we are writing here into DP2. So here we are integrating. So while integrating, we take this as 0.05 P2 squared divided by 2 plus 16 P2. So here lower value and upper value we are taking. Just substitute this upper value and lower value minus the lower value. We are getting the answer here. Fuel cost function 2 as fuel for cost F2 as 741.0897 rupees per hour. Now they asked what is the loss incurred. Loss incurred is nothing but profit gain. Loss incurred or profit gain. So what is the profit gain to the through considering the transmission loss, or otherwise in other scale we can tell that as loss incurred, profit gain or loss incurred. So that is nothing but F1 plus F2. So this F1 plus F2 is nothing but loss incurred by scheduling generators without considering the losses to considering the loss. So that's why without considering losses, we have taken as lower scale, and with the considering losses, we have taken in the upper scale in the while integrating. Okay, so that we have taken. So while taking this, we already calculated F1 and F2. That is minus 514.6908 plus 741.0897. So simplifying it, we are getting the profit gain or loss incurred as 199.3989 rupees per hour with respect to scheduling generators without considering losses to considering losses. So that is the loss incurred. This is the loss incurred. That is 199.3989. That is approximately 200 rupees per hour. That is the loss incurred for the data given in the problem. This is how you need to do. Suppose in the same case, they asked loss incurred with considering loss. Then you need to take in the reverse manner. So you need to take with the considering losses, whatever you calculated, that P1, P2 value, you need to take in the downward scale, and without considering losses, you need to take in the upper scale. That time, this data, this answer may differ. This answer may differ because if you take it in the upper scale, this will become positive. This I think this value will come here and this value will come here. So this will come in the positive values. So here you will get positive values. That is 541.3 is 6908, and F2 also I think almost this will come in the negative. Okay, this will come in the negative. So reverse we'll get, that is minus 7441 and plus 471. So if you do this also, you'll get minus 199.3989 rupees. So that is the loss incurred when it is in the reverse case. That is with the loss incurred by scheduling the generators with the considering losses to without without considering losses. So this is how you need to calculate. If the question is asked in the either direction, you need to change the calculation. That is how you need to do this problem with the transmission losses. So you need to very, very careful. You need to read the data in prior. So without reading this problem blindly, if you solve, then the answer may goes wrong. If you take the lowest scale value while integrating, if you take the lowest scale value and upper scale value like in the reverse manner, then the financial loss incurred will come in the reverse manner. So the answer will be wrong. So here you need to study the problem correctly and you need to solve this kind of problem. I think this is the second problem we are doing in the similar case in our videos.